time gaps. Now we are going to look at the time series of macroscopic quantities. And the takeaway of this section is that if we have multiple detectors, we can use multiple detectors at the same time and look at the time series of different macroscopic quantities, including flow, speed, and density, etc. And that can tell us a complete story of what is happening over different weekdays, over weekends, and how is traffic breaking down, and the types of traffic congestion, as mentioned here, oscillatory and essentially stationary traffic. I think we have previously discussed the definition of stationarity, or we'll do that today. I think we have discussed it before. So stationarity is just to remind you a concept from statistics where we are assuming that the distribution of whatever variable we are interested in is not changing over time. So for example, if the distribution is created using normal distribution, we have two parameters, the mean and the standard deviation. And those two parameters are not changing over time. So the distribution remains the same. And in this particular context, we are talking about the variable of speed. So in this section of the time series, we have these plots. On the top figure, we see speed over time, then the flow over time, and then the density over time. And we can see that there is a drop in the speed, a drop in the flow, and an increase in the density at this point in time. This is around 7:30 a.m. So the question that is asked in this section is, why is it wrong to conclude from the time series in figure 5.8 that the traffic breakdown occurred at around 7 a.m.? So looking back at this is 7 a.m. And the question is saying, why is it wrong to conclude that traffic is breaking down around 7 a.m.? So apparently, looking at just a single detector's time series of speed, flow, and density, it does seem that the traffic breakdown started around 7 a.m. And clearly at 7:30 a.m., there is a big drop in speed as well as in flow and an increase in density. So why is it wrong to conclude that? It's because there could be multiple explanations of what is happening as well as where it is happening, both in time and in space. So if we have multiple cross-sectional data, so we have multiple cross-sections, loop detectors at certain intervals, and we get data from them at the same time, then we can compare what is happening upstream and downstream, and that tells us a complete story. Looking only at a single detector's data may be misleading, and that make us mislead into the conclusion that there is a breakdown starting at 7 a.m. So in this section, they have explained that there could be two possibilities. One of the possibilities is, although that figure above is about highway, if we see the same pattern around an intersection, then one of the explanations could be this. We have these trajectories, these black lines, these represent trajectories, and we can clearly see on this time and space diagram with the detector right over here, this is the cross-sectional detector. We see that on this end, when the trajectory is moving at time 0 in our observation, it is faster because the slope is sharp, and then it slows down here. In this area, it slows down much earlier. This is a different trajectory. And then later in time, it slows down relatively later. But then it does slow down and then again gain speed. This is happening to all the trajectories. We are only seeing three, but this is happening to all the trajectories of all the vehicles in this area. These lines, these boundaries, they represent the point when they slow down. So this one slows down here, this one slows down here, and this one slows down here. And if we join all of those points where the trajectories change slopes, that gives us this boundary. And this boundary is called as a jam front, this thing. So in this figure, what they're saying is it may be that downstream, which means that down on the road, there may be a jam front or there may be congestion because there's an intersection here. Because there's an intersection due to the red light, vehicles have to slow down. And as a result, that slowdown will move upwards towards upstream of the traffic. And so that would slow down vehicles over here. So if we have a single detector, it will only see this. It will only see that some of the vehicles are fast, some are slow right here after some time. And so we would conclude that the um, congestion and the breakdown started here. But that's not the case. We can see that congestion is happening here as well. And the cause of the congestion is spatially distanced from this point. Another possibility is if there's an accident, and this could happen either on an intersection or on a highway. And there, the problem is downstream jam front and then downstream congestion. And so if there's an accident, vehicles need to slow down. Or if there's a blocking vehicle, which is also mentioned in this section, that could be a large truck, which is slower than the cars. That is also creating a bottleneck, but it is a moving bottleneck. As a result of that, it will continuously increase or create the breakdown downstream as it moves. So there are multiple possibilities. That this question was here as well. Can we at least conclude from the figure that vehicles near the cross section at 7 a.m. decelerate, or that vehicles near the cross section at 8:30 a.m. accelerate? If not, what are alternative explanations for the observed patterns? So we have seen the two alternative observations. One possibility is that there is an intersection and there is a downstream breakdown, and that is moving upstream. The second possibility is the same thing due to accident, or another possibility is that there's a moving bottleneck, which is like a large truck. So in that case, the breakdown will happen downstream and continue to happen in downstream. So this is what is explained in the solution here. And later in this section, spatiotemporal analysis, they explain using multiple detectors. So previously we only saw one, but now we have these 5 detectors, actually 4 detectors, which show that there is this roadway where there's a merging traffic here. Upstream of that, sorry, downstream of that, there is an intersection, which is mentioned right here. This is the name of the intersection. And so because of that intersection and because of the merging traffic, vehicles would change lanes and there will be some congestion and traffic breakdown. That traffic breakdown is clearly seen here as detected by these detectors. In, in, in the beginning, there is a higher speed. So these purple speeds are around 80 to 100 kilometers per hour. And then they break down. But if you look at these minimas of each of these time series, we see that they're moving in time. So this is happening at 8 a.m. when there is a slowdown observed by D10. And then here at D07, this is happening at around 8:10 a.m. So that is moving in time. And so if we connect them, we get these lines. And these represent the negative speed, also called as the traffic wave, the speed of the traffic wave, which is happening due to these breakdowns that is happening upstream. So that was the actual explanation of the question that was asked in the previous section. Any questions or comments at this point?
Yes, I have a question.
Yeah,
So the breakdown starts at D10 at around 8 o'clock, and then it
yeah,
arrives at the detector D07. This seems like around 10 minutes later.
right.
So this is like quite a long time for a breakdown to propagate downstream. What could be the explanation for this thing?
So there is some distance here. So we see these markers that represent the distance as well. So this is 473 and this is 476. So the distance between them is 3 kilometers. So that's one of the explanations. And also the breakdown has actually started earlier. As I mentioned, that there is an intersection here and there's merging traffic here. As a result, there is traffic breakdown. So that is the cause of the breakdown, and it is then traveling, and it is detected by these vehicles. So some of these vehicles would slightly slow down. Then in here also, you can see that there is some slowdown, right? But the authors did not discuss this particular detector. They started the discussion with D10. But we can clearly see that there is some breakdown over here as well. There's some slight breakdown over here as well. We wouldn't call it as breakdown, but a slowdown, I would say. So it is traveling upstream, right? And it's gradually traveling. But here we see very clear patterns. Here we see these troughs of the time series, right? And the same shape is then propagated throughout the time series of these cross sections. So I would say that because the distance between them is 3 kilometers and there are 10 minutes involved between the time when it is observed here until the time when it's observed here. I think it's slowly building up and then slowly slowing down.
Okay, yeah, right.
Okay. All right. So here they mentioned that you can estimate the wave velocity, the velocity of these of the slopes of these lines, these black lines that are connecting these minimas. And we can do that two ways. We can do it by just visually inspecting this and then taking a slope. We have the distance, we also have time, or we can use the formula of the speed cross correlation functions. So correlation is a concept from statistics, which looks at the linear uh, correlation between the two variables, which means that as one variable increases, what happens to the other one? We assume that it linearly changes with the other variable. And so the speed cross correlation function is used for two detectors. So for example, if we talk about the detector D07 and D10, which are labeled here, D07, D10, and we are only looking at these two time series. So this is for D07 and this is for D10. For these two time series, we have multiple data points, as we can see in the figure, and we can estimate the correlation for these two detectors' speed. So that is represented by K for one detector, for example. That could be D07 or D10. So let's say K is D10. So that is the time series of the macroscopic speed. In this case, it's the arithmetic mean speed. And then we also have the time series of the other detector. In this example, that would be D07. So we have D10, D07, their speed, time series, and then we are finding their correlation. So if we use this correlation coefficient, that tells us the speed cross correlation function that can help us determine the um, wave velocity. Another way that they've shown here is this formula where if we look at the distance, delta xkl, and the time during which, for example, let's look at this one. So for D10, this is around 8 a.m., just before 8 a.m. And this one, the minima here is at almost 8:10 a.m. So the difference between them in time is 10 a.m. The difference between them in distance is 3 kilometers. So if we plug in those values for delta x, it's 3 kilometers. For tau, that would be uh, the 10 minutes or so. That would give us the wave speed, the speed of the traffic wave. And here they define it as delta x scale is the distance between the detector stations. I think there is an example here as well. Let's see. I think they mentioned problem, or maybe it comes later. Anyways, um, so next section is about speed density relation. And this is what contributes to the fundamental diagram discussion. So speed density relation is about these plots. So let's look at this one first. I'm going to zoom in, and the x-axis here is density, and the y-axis is the macroscopic speed. Now, this macroscopic speed, again, is the arithmetic mean speed, which means that you have a detector. On that single detector, for a time delta t, for example, for 60 seconds, you count how many vehicles are moving, how many vehicles are crossing that detector, and also find what is the speed of each of those vehicles. We have previously discussed that that is available to us directly from the detector. So those are individual speeds. If we take all those speeds and then take an average of those speeds within the observation of 60 seconds, that will give us a single data point of speed, the macroscopic speed, sorry. And if we then estimate density using the previous discussions we had on estimating densities, it could either be flow divided by this macroscopic speed v, or it could be flow divided by the harmonic mean speed, depending on the stationary versus non-stationary conditions. We have different formula and we discussed in the last session. So once we know what density is, which is also a macroscopic quantity for those 60 seconds, and we also have this macroscopic speed, we can now have individual data points representing those, and we can then plot them. So these red points represent all those points. These are averaged over all the lanes. And this is, in this case, particularly for detector number 26. And then there's this black line, which is fitted on these data points. The black line is not coming from the data. It is just a model fit to the data. So my question here is, what do you see in this line? What is it telling us? What is the pattern that you detect here? Any ideas?
As density increases, the speed decreases.
Yeah, so as we see, as density increases, as properly put today, the speed decreases, which, if we think about it intuitively, makes sense as there are more vehicles in a particular delta x. Their speeds have to be slowed down because otherwise we won't have as many vehicles together. But there is this initial part which shows us that there is an increase in this speed when the density is moving from very small value. It's definitely above zero. No data point here is exactly at zero, because if there is no density, then there is no vehicle there. But we see that as density increases slightly in the beginning, speeds increase. Does that mean when density is almost zero, the drivers themselves are disciplined enough to not use the maximum speed they can? The maximum speed comes later at a higher density. Why don't they go at the highest speed when there's almost no one on the road? So this is a question that, looking only at this plot, would come up. The explanation is on the right. This is showing us the breakdown of the same data points using the time. So we have 0 to 6 hours represented by these purple data points. Then we have 6 to 19 hours, so which means 6 a.m. to 7 p.m. in the evening. These are the red data points. And then 19 to 24 hours are the black data points. So here we can see that there essentially is two clusters of the speeds on the same range of density. We see some of the speeds are just above 80 kilometers per hour, and some of them are at 100, some of them are just above 100 and 120 between them. So these represent, as the chapter explains, the speeds of trucks and cars. And for the other two data points, we see the same uh, pattern as discussed here. As density increases, the speed decreases. Only in this part, we see uh, this kind of cloud, and this representing vehicles moving at their desired speed. So they don't really have a correlation with density here because density is very small, so they don't really care. They go at their desired speeds, and they're limited by, obviously, the speed limit. Even if the car drivers would violate the speed limit, they would still be between 100 and 120 kilometers per hour. Truck drivers mostly follow the speed limits. They may also violate it. So maybe some of these are truck drivers, but they are around or between 80 to 100 kilometers per hour. But for other two sections, we do see that for 6 a.m. to 7 p.m., we see this relationship where the flow is a bit smaller, which is expected because uh, between 6 a.m. to 7 p.m. we do see some peak hours. And then we also have 7 p.m. Uh, to the mid of the night. And in that case, the flow is a bit higher because there isn't as many vehicles on the road. We also see then further breakdown of the data points by the left, middle, and the right lanes. And so we do expect that right lanes are the slowest. That's why we have the smallest speeds over here. And then further breakdown with the type of the lanes as well as the times. This line that we see here, when we are not discriminating between the times, when the data points were generated, this line is called as the speed density diagram. And so this is a theoretical equilibrium speed, which we can determine using, so this complete plot is not the theoretical equilibrium speed, sorry. This part where the speed is increasing, this would represent the theoretical equilibrium speed. And the whole line here, the black curve, this is the speed density diagram. So let me read this so that it is properly uh, mentioned. The speed density diagram, or I should read from here. When locally averaging the speed density scatter plot for different density classes, it is possible to extract the speed as a function of the local density. The speed density diagram, which often is interpreted as the theoretical equilibrium speed, V of rho, or more precisely, the homogeneous steady state speed. Now they have defined what homogeneous means and what steady state means. Homogeneous means that there are no changes along the road, such as ramps or changing speed limits. So essentially, the road geometry remains the same. And steady state means that there are no temporal changes of the speed distribution, including its average, V of rho. So this definition of steady state seems to me is the same definition of stationarity, which is a statistical concept. But the concept of steady state is a traffic flow concept. So again, steady state refers to no temporal changes of the speed distribution. Speed distribution would remain the same. So this is why this black line is theoretical. This is just fit to these data points, and generally people have figures, which I'm sure we will discuss in the part of traffic flow modeling, where they have models that represent these lines using different equations. Okay, any questions? One term that they have mentioned here is the Simpson effect. And so the Simpson effect is this thing where once we broke down the data points by time, we see a completely different pattern. That's what Simpson effect means in statistics. And other than that, they also mentioned that you can determine the desired speed from this when the density is very low. Then you would say that the higher speed that you're getting here, those are the desired speeds of the drivers. And this is also important that we conclude that speed density scatter plots depend on the vehicle fleet, which means the traffic composition. Other factors are regulations, variable speed limits, external conditions, which also includes weather conditions. And this also applies to flow density and flow speed plots that we are going to discuss next. So questions, any confusions? Okay, let's now discuss the flow density diagram. So let's first take a look. This is an example of a flow density diagram, and it is the two color data points are for two different locations, one for A8 and the second for A9. So in its idealized form, that is the steady state equilibrium of identical driver vehicle units, flow density diagrams are called as fundamental diagrams. So if you look at this plot, we have two sets of data points, the red and the blue ones for two different roadways. On x-axis, we have again density, and on y-axis, we have the flow. This is a macroscopic flow. And if we fit these two lines, and it's not necessarily a fit to the data points, it could be if this is the pattern like we see here, but it also could be a theoretical equation that represents the flow density diagram. So these fits or these lines, these represent the fundamental diagram. Fundamental diagram would mean that your traffic flow contains identical driver vehicle units, which obviously is not possible in real life. And it also assumes that there is steady state equilibrium, which means that the speed distribution is not changing over time. It's remaining the same because everyone is going at the same speed, not accelerating at a given gap. They are at a given gap that they're keeping from the lead vehicle. They are moving at the same speed throughout. That would mean fundamental diagram. Which does not mean that the speed cannot change. The speed can change, but if the speed changes, it is changing based only on the gap that they're keeping. So in free traffic, which is represented by this left line, in the free traffic, we have a clear explanation here that this is the free traffic branch of the flow density diagram. And on the right, we have the congested branch of the flow density diagram. And if we only look at the lines, we say these are fundamental diagrams. If we look at data points, we say these are flow density diagrams. And we can define certain things using these diagrams. We can define the desired speed, which is equal to the asymptotic gradient of the flow when density is zero. So when density is zero, we are right here, which means that we are talking about this free flow or free traffic branch. If we take a slope of this, that will give us speed, because remember, density is equal to flow divided by speed. So if we take a slope here, that would give us the speed, and that would be the desired speed. We can also estimate the mean speed for a defined density by getting the slope again. For other parts of the plot, we can use this formula to get the mean speed. We can also get the maximum value of the flow, which is called as capacity. In this case, that is this point for the red data points and this point for the blue ones. So that is the maximum flow, also called as capacity. And then we can also get the inverse of the smallest non-zero density, rho max, which represents the average vehicle length plus the average gap between stopped vehicles. In this case, these are the row max for each of these two roadways. And this represents, if you recall from our previous discussion, density is equal to 1 divided by average of distance headway. Vehicle length plus gap is also equal to distance headway. So rho max then represents average vehicle length plus average gap. Okay. Any questions? Okay, and then we can also get the mean time gap, capital T, which can be determined from the negative slope of the flow at large densities. Then the slopes of the flow density diagrams also allow to read off the propagation velocities of jam fronts, but this part is not very clear in this section. So they are going to talk about both points 5 and 6 in chapter 9. So here again, they reiterate that the fundamental diagram describes the theoretical relation between density and flow in stationary homogeneous traffic. See, they now use the word stationary. Previously, they used the word steady state. They use it again here. That is the steady state equilibrium. So steady state equilibrium is the same thing as the stationary conditions. That is a concept from statistics. And it's also using identical driver vehicle units. The flow density diagram, on the other hand, represents aggregated empirical data that generally describes non-stationary heterogeneous traffic that is different driver vehicle units, which are far from equilibrium conditions. They also mentioned that if you use the hydrodynamic relation of rho is equal to Q over V, there could be some bias. So instead, you can use this formula, Q star divided by harmonic mean speed. Q star is equal to 1 divided by the summation of flow, I think, the microscopic flow. We have previously discussed the equation for Q star. Let's see. Here is 512. Yeah, so this is the average of 1 divided by the time headway, or the average of the microscopic flow. So it's not a sum, it's the average of the microscopic flow. Easier one for me to remember is this one. It's the average of 1 divided by the time headway. So this, according to the discussion, is a better approach to estimate the density. Okay, so now we are in this discussion of using density and flow, so flow density plots, and this is simulating a highway traffic. So to do that, how they generated these plots is from a simulation using their own software called as MobSim. So let me now show you that. I'm going to stop sharing this screen and let's share the complete screen. Okay, so here if we go to MovSim GitHub, this is the main repository of the software. And I have put everything in the repository that shows how to install it and how to run this particular simulation. So let me increase the size here. So the first step is to install Git, but this is only needed if you want to clone this repository using Git. For now, you don't really need Git. You can just download it. You can go to code and then download zip. If you have Git installed or you want to install it, you can then use this command to clone it. Cloning means downloading the folder. Cloning is just the terminology from Git. So let's go back here. You also need to install Java SDK, Software Development Kit. You also need to install Apache Maven. This is the software that is going to build the MovSim software for us. What we see here is just the source code. So it's not going to work out of the box. You need to have it built. And to build it, you need this. Then you need to install the new plot because all of these plots that they have created are using the new plot command. And let me see if we are live or not. Okay, we are. Okay. And then um, definitely new plot and Git are optional, but because they use that, I'm also using that here. Now for the simulation, they have, if we go to the repository, if you go to the sim folder, and then go to book scenario simple on ramp. This is the folder that contains all the scripts for running the simulations with different car following models. The one that they have used here is the IDM uh, model. So we are going to use that here. So this is the command. This is the Java command. Once it's installed, you can run it. So you're going to type Java and then dash jar. And then within the viewer folder, there's a target folder. And then there's this file. This is the one that is built once you run mbn install after cloning MovSim. And so this file is generated. Let me show you that file. So if you go to MovSim right here, uh, if you go to viewer, target, and then this is the file that is generated once the MovSim software is built. And this is going to basically run our simulation. So we tell it what files we want to run. So we want to run this file onramp underscore idm.xprj. And this is coming from, again, the book scenario simple on ramp. Let me first explain to you what that scenario does. So if we go to the figure 12.8, um, this is the result in chapter 12 for the intelligent driver model, and it's showing us a similar figure. And if we now go to chapter 11, this is where they have explained that particular simulation. So here, um, the fact sheet of dynamical model characteristics, they have this section highway scenario, and within highway scenario, they explain what the scenario is about. So in this case, they have lane changes allowed, which take place in 1 kilometer long merging zone of the on-ramp centered at axis equals to 0, right? So there is a long single freeway lane, and then there is a merging zone which is 1 kilometer long. And then uh, the peak value of the flow is 2,200 vehicles per hour. On the on-ramp, the flow is 550 vehicles per hour. So it doesn't change on the ramp, but on the main highway, it does change. So how do we know how much flow there should be? That is provided in the file. If we go to on-ramp idm.xprj, here we can see that it provides the flow of 0 at time 0, starting point. The flow is 200 vehicles per hour. And then at time 1500 seconds, the flow is 2200 vehicles per hour. Initially, the speed is 30 meters per second, which is just below 120 kilometers per hour. And then it goes to 22 meters per second. And for the ramp, the flow remains to 550 vehicles per hour. So we need to run this, and we need to run this in the same directory as MovSim. So I'm going to copy that here. I'm going here, go to the main MovSim directory, and then right click, click on open in terminal, and I paste that here, press enter. So it's going to launch this GUI for us and start the simulation. If we zoom in, this is showing us this part. Interestingly, we don't really see the on-ramp here. And that's the choice that authors made. Although they are simulating the on-ramp, physically we don't really see it in this simulation. So it takes some time to run it. You can see it here. Once this is complete, this progress bar would show that the simulation is complete. And then once it is completed, it would then generate multiple detector data sets, because there are multiple detectors on that roadway upstream of the on-ramp. So they will be generated here. And once they are generated, then the authors use this file. This is all of these commands are the new plot commands that would use the data that I just showed you and then create the simulation. So I've already done that. And after that, if I go to sim and then book scenario simple on ramp and then plots, this is where we can see those plots. I'm going to open this, but it should not be this one, but it's okay. This one also works. And let me zoom in. So this is what the plot shows us. Now let's take a look at what we saw in the chapter. So I go back to the analysis of cross-sectional data, and at the very end of this chapter, we'll see those plots right here. So this is showing us, the first plot is showing us time on x-axis and distance from the on-ramp. So 0 means that this is exactly on the on-ramp, and this is upstream of the on-ramp, and this is downstream. And so upstream, because of the traffic, now if you take a look here, uh, we see that vehicles are slowing down a bit, right? As they're moving along the ramp, they're slowing down a bit. And over time, you will see even more slowing down, and this will become a bottleneck. So that is causing the upstream congestion. So the red and orange lines or colors here represent uh, traffic breakdowns. The first one here is using the formula of flow of 1 divided by the average of time headways. That's the formula of the flow that is used on x-axis here, and on, sorry, y-axis here, and on x-axis we have density, which is estimated using Q over V right here, right? So the flow is defined like this. So that's the plot, right? So what do we see here? We have the fundamental diagram, the black line. We also have these data points for at 1 kilometer from the on-ramp, 3 kilometer, the triangle, 5 kilometer, this orange square, and then 7 kilometer, the blue square. All of these represent the points. If we first look at the fundamental diagram, this is showing us that this is the free flow branch of the fundamental diagram. Remember, fundamental diagram represents identical driver vehicle units, and also assuming that the speed distribution is not changing over time. And so this is the free flow branch, and then this is the congested branch. But the actual data points, although are plotted on top of the fundamental diagram in the free traffic, in congested traffic, it's not even close to the congested fundamental diagram. Here we see these point clouds, and we see that the maximum density that they go to is less than 60 vehicles per kilometer. But these sets of plots also tell us that using different formula for estimating flow and density will give us different results. You can clearly see these different results. This last one here, this is directly from the detectors that are available in the simulation. This is the flow using the definition of flow, the number of vehicles at a particular location for a given unit of time. And the unit of time here is 60 seconds. The density rho is the number of vehicles in a kilometer, right? So this is directly available from the detectors in the simulation. And these are making very similar figure like the fundamental diagram. So we have the free traffic and then we have the congested traffic, this line. Yes, there are some outliers here, but I wouldn't say these are outliers. There are other point clouds here, but we see the clear pattern, which is just like the pattern in the fundamental diagram, although the density is smaller than what the fundamental diagram suggests. But then in plot C, we have flow Q, again estimated as this formula, versus density using flow divided by harmonic mean speed. So this is C. This is what we get. A different interpretation here because the plot is different. In part D, we have flow, which is Q star. So this is the average of 1 divided by the time headways. And the density is Q star divided by harmonic mean speed. So that's D. Right? Again, very similar pattern like the fundamental diagram. So this seems to be a good estimation because we're using harmonic mean speed, which we know is a better representation of space mean speed, and flow is also a better representation of the actual flow. And then we have part E, which is using the flow as this definition and density as Q star over VH. So every single of these plots give us a different result. So that's why it's important that we know exactly what definitions we are using for flow and density. So now if you look at this, you can clearly see that the traffic breakdown is moving upstream, right? This is now 1 hour 34 minutes of simulation time, and it takes 2 hours for the simulation as specified in the simulation settings. So this is the result that we get. This is unlike any of the plots that we saw in the chapter. And I have already emailed the authors as to why do we see these differences. I have made sure that the IDM model parameters that we have used are the same as mentioned in the book. It's in table 12.2, I think, in chapter 12. So we are using exactly the same things, but we are getting somewhat different results. These triangle data points represent just the most closest detector of 1 kilometer. So here we see a higher density between about 62 or like around 50 to 70 vehicles per kilometer. So in general, qualitatively, the result is the same, but we do see a higher density with these data points when we run it in MorphSim. The second part that I want to show is reproducing the same thing with Sumo, which I find much easier to follow because I can also see the network much clearer. It's unlike what is shown here where we don't really see the on-ramp. So I'm going to close this and it would automatically close this as well. And let's see if anyone has any questions first. Okay, for Sumo, we need to switch to that other project. Let me open the folder. Should be called as Sumo book scenario simple on ramp. And so I put everything in this README. And because this is also available on GitHub, I can show that here in the README. So this is the result with Sumo. And I have tried to use the same definitions. As you can see here, this is directly from the flow and density obtained from the detectors. And so you can see that this is more or less following the fundamental diagram. Remember, simulation has identical driver vehicle units. We're not changing vehicles, we're not changing the drivers. So that's why the data points are also around the fundamental diagram. To reproduce this at your end, you need to have Python installed. You also need to have the UV framework to uh, to as a package manager in Python. Once you install UV, you can then just type UV sync in your IDE. So if I do that in the terminal UV sync, it will install everything that we need from Python. And then actually in this case we are not really using Python, so you can completely skip this. Um, for generating the network in Sumo is composed of two things: network nodes and edges. Nodes means junctions or intersections. Edges means roads or streets. So I created the same thing with the help of Claude AI, and I provided these nodes, individual nodes. So I called it a start. The X location is minus 9,000 meters. Y is at 0. Type equals to priority means that in this case it doesn't really apply because it's highway, but priority means that if you have um, an edge with a higher priority and an edge with a lower priority in terms of right of way, the one with the lower priority will have to wait. The vehicles there will have to wait until the vehicles on the higher priority edge have cleared. So we do that. Uh, we generate those nodes for all of the uh, network, and then we also generate edges. For example, I call it as edge up EUp, and that goes from the node start to the merge start. Let me actually open this in a utility that is available once you install Sumo. It is called as netedit. So I open netedit, and then I want to open the network. I want to open network, and this is onramp.net.xml. This is available in the GitHub repo within the network folder. So it is right here, onram.net.xml. So the node, the edge, and the connections, these three files are needed to generate the net.xml. Or you can just use this GUI, this software, NetEdit, to generate it by hand. So you have both options with Sumo, which is pretty great, I think. So here we can clearly see this on ramp, 1 kilometer long on ramp. This is the section E up. If I zoom out here and then go right here, this is the section E up. So you see here, and this is with the start node, and then we have in the middle, right here, the merge start node. And this one is the ramp start node, right? And this one is the E ramp edge. So using those files, if I go back here and go to the README, we have the nodes, we have the edge files, and we have the connections that tell us which lanes in one edge connect to what lane in the other edge. For example, in the first edge to the merge edge, we are connecting lane number 0. There's a single lane in EAP, so it doesn't really matter. It's always lane number 0, which is the first lane. And then it is connecting to lane number 1, which is the left lane in here. Here we have two lanes. So this is, if I right click here, this is the emerge 1, which is lane number 1. And then right click here, this is emerge 0, which is the right lane. So that's how we specify the connections. And then if we run this command, net convert, with all of these files, and we ask it to create an output file called this, it will generate the output file of onramp.net.xml, which I have opened in front of you right here, which generated this network. And then we also need to provide the route where each vehicle is going. Looking at this again, obviously we enter the vehicles from the E up and also from E merge, and then they enter here. They enter on this lane or either on this lane, and then they leave from this final edge here. This one is called as E down, right? So that's what the route should be. So we first create a vehicle type. In the vehicle type, we tell it to use the car following model of IDM. The length of the vehicle is 6. This is using the same parameters from MorphSim. Min gap is 2.5 meters. Maximum speed is 33.3, which is 120 kilometers per hour. The acceleration parameter of IDM is 1.1. Deceleration is 1.5. The reaction time is 1.2, and it's actually not reaction time, it's the IDM parameter t, and the delta is 4, which controls the acceleration. Sigma is equal to 0 means that all driver vehicle units are identical. Then we define the route. The main route will contain those three edges, up, merge, and down. And the ramp route will start from the ramp edge, then go to the merge, and then to the down. And then we have the flow specified here. So we have the main flow where we tell that it begins at 0, ends at 1500 seconds. So this is mainly following the same explanation as in the MorphSim. So we have main flow and ramp flow. Then we put the detectors, and there are two types of detectors. There's induction loop detectors, which are cross-sectional. Similarly, there are another cross-sectional loop detectors, which are called as instant induction loop detectors. If you recall from the chapter, we discussed that there's single vehicle data. So if you recall from the chapter, the uh, detectors also get single vehicle data. So instant induction loop in Sumo will get the single vehicle data and give it to us. And the aggregated data is given by induction loop detectors. And then to create the flow density plots, I have this Python file in the same repository. So if we want to run this simulation, we go to the relevant folder and then double click this file. This is a Sumo configuration file telling it about everything that we have created, and then we run it. So once we run it, let me also increase the delay here so that we can clearly see it. So you can see that the bottleneck is then generated here. And if I change it to real world, it would then look just like MovSim, where we can see that there is traffic breakdown. So if we continue to run this and then run the Python script, it will then generate what we have seen here. These are the results that are generated. So we can go into more details of how this line is created. Data points you know now are coming from aggregated values from the induction loop detectors. And then I use the same definitions as explained in the chapter. But the line itself is a theoretical line, which is based on steady state equilibrium conditions, which we can discuss the next time. So thank you so much.